Good afternoon and welcome to Hand-Wavy Chemistry. When chemists publish their research, one of the bits of data they include is the percent yield, which compares the amount of material they were able to isolate to how much they would have got if they lived in some kind of magical Christmas land where molecules did exactly what we want them to do. And for some reason, many people, when they start learning chemistry, assume that all reactions must have at least an 80% yield, which is absolutely not the case. For example, there is an undergraduate laboratory experiment where students are tasked with synthesizing a porphyrin. And many of them, when they calculate the percent yield and find that it is only 10 to 20% at best, write in their lab report, "I must have made some mistake because this yield is far too low," when actually it makes perfect sense for this type of reaction. But before I talk more about that, I want to discuss a different reaction, one that was brought to my attention due to its inclusion in a homework activity. This activity involves looking at a reaction and predicting what the major product will be, making sure to correctly assign any stereochemistry if applicable. And the final example on the worksheet was the reaction of 1-bromoethyl cyclohexane with sodium hydroxide. Now, the first thing that I noticed is that despite this activity being concerned with stereochemistry, and this molecule having a stereocenter, the configuration at this position was not specified. But perhaps that is a hint. And indeed, the expected answer of ethylidene cyclohexene does not exhibit isomerism. But how is this molecule formed? Well, the lone pair on our base comes in and removes a proton from the tertiary carbon center. And as this proton leaves, the electrons from that carbon-hydrogen bond, they move over, forming a carbon-carbon double bond, and the bromine gets kicked out. But this isn't the answer that the student came up with. They had that lone pair attacking the carbon with the bromine bound to it directly, breaking the carbon-bromine bond and forming 1-hydroxyethyl cyclohexane. And both of these mechanisms are totally reasonable. The preferred answer comes about through an E2 elimination reaction, while the student's answer is an SN2 nucleophilic substitution reaction. But how can we tell which one will be the major product? Well, as we learn about chemistry, we're given guidelines about what type of conditions will favor which particular product. But if we want to take a sledgehammer to a walnut, we can use frontier molecular orbital theory. Since our 1-bromoethyl cyclohexane is acting as an electrophile in this reaction, frontier molecular orbital theory says that the most important orbital is the lowest unoccupied molecular orbital, also known as the LUMO. So let's take a look at it. We need the lone pair on the oxygen to either hit the blue orbital around the proton to trigger the E2 reaction, or the red orbital on the carbon atom to trigger the SN2 reaction. And we can see that that proton looks much easier to hit, justifying the answer that the E2 is the preferred process. But what about that other proton on the other side? That also looks kind of easy to hit. And indeed, this is also a possibility. And if the base were to remove a proton from that methyl group, it would still be an E2 elimination reaction, but now we would have ethynyl cyclohexane as our product. So how do we know which one is going to be the major product? Enter Alexander Zaitsev. Zaitsev's rule states the alkene formed in greatest amount is the one that corresponds to removal of the hydrogen from the beta carbon having the fewest hydrogen substituents. So the tri-substituted alkene should be our major Zaitsev product, while the monosubstituted alkene should be our minor anti-Zaitsev product. And the reason for the selectivity comes down to thermodynamics and the energy levels associated with the various transition states and final products themselves. And at this point, I have a confession to make. When I calculated those molecular orbitals before, I cheated. I arranged the molecule in such a way that the bromine was in perfect alignment to do the E2 reaction. But bonds can rotate. And so if we redo the calculation with that bromine no longer in perfect alignment, we see that at least some of the time, the preferred E2 Zaitsev reaction cannot proceed because the orientation is wrong. And this is why when we do this reaction, we shouldn't expect a 100% yield of the preferred product, but rather a mixture, with the preferred product being the major product and the other two also present. But guess what? We're not done yet, because all of the reactions we've considered so far have occurred in a single step, and there is another option available. For you see, that bromine atom, it could decide that it's sick of being part of this molecule, take its electrons and leave. And when it does so, it will generate a carbocation, which has a trigonal planar geometry. And so any reactions that now occur at this position will scramble the stereochemistry. And you might be saying, so what? There was no stereochemistry specified in any of our answers so far. Which is true, but there's something else that can happen in this molecule. For you see, right next to our secondary carbocation, we have a tertiary carbon, which means we can have a hydride shift. One of those hydrogens can slide over, generating a thermodynamically preferred tertiary carbocation. And now we can get some different products. When our base comes in to remove a proton, there are 3 CH2 groups next to that carbocation for it to choose from. If it takes from the ethyl group, well, then we just get back to our ethyladene cyclohexane. But if it takes from one of the groups in the ring, now we're going to get 2-ethyl cyclohexene as a product. And this two-step elimination reaction is known as an E1 reaction because its rate law is first order. So are we done? No. Because when we had that carbocation and we brought in the hydroxide ion, rather than taking one of the protons, it could have reacted directly with the carbocation itself in an SN1 nucleophilic reaction, giving 1-ethyl cyclohexanol as the product. And at this point, we are basically done. The only other few sensible reactions would have to involve very unlikely events, like the bromine coming back and reacting with the molecule in a different position, or a hydride shift to a less stable carbocation. But yeah, they would only be incredibly small trace amounts, if any at all. But what I hope this highlights is that there are very good reasons why reactions don't give 100% yields. Although we can certainly predict and rationalize what the major product will be, all of these other side reactions, even if they're only producing small trace amounts of impurity, will lower our overall yield. Now, what about that porphyrin reaction? The porphyrin molecule was being constructed in a stepwise manner out of 4 subunits. And if we do them one at a time, 1, 2, 3, 4, close it up, it all makes perfect sense. But the reality is a lot more messy. Imagine if we had 2 of those units together and 3 of those units joined together, and then we brought those together. Now we have 5 units and we can't close the ring. But this 5-unit molecule can continue to react, using up more and more of our subunits, lowering the overall yield. So what's a synthetic chemist to do? Well, one option is to use metal templating. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.